Zero to production genomics in 14 days. The challenge, intimidation versus execution. When I first looked at this project, it was intimidating. To build a production-grade genomic analysis pipeline, you typically need the kind of domain expertise that takes 15 years to acquire. But we didn't have 15 years. We had exactly 14 days. I have a PhD in math, but 2 weeks ago, I knew zero biology. Now, the goal here wasn't to replace a biomedical engineer. A veteran in the field could have done this faster. But that expert's time is incredibly valuable. The goal was to see if I could use an AI-directed workflow to take just 3 or 4 hours of a domain expert's time and handle the rest myself. Today, I'm going to show you the exact technical meat of how we went from zero to a modular system processing thousands of RNA-seq samples on AWS Parallel Cluster. Phase 1, the transcript to spec workflow. The workflow started with expert extraction. I sat down for a few sessions with a domain expert. We captured everything as raw audio, ran it through our transcription utility, and then I fed those transcripts into the AI to help me understand the intent. The result was a comprehensive technical guide. We identified our target, dataset GSE 193677, a massive IBD study with nearly 2,500 samples of Crohn's and ulcerative colitis biopsies. Before writing code, the AI helped me synthesize a formal spec. We'd use Salmon for fast quantification, fast QC for quality control, and a modular architecture. I took this back to the expert for a quick sign-off. Because the AI had the expert's intent from the transcripts, the sign-off was nearly instant. We had a roadmap before we had a single line of bioinformatics code. Phase 2, the pipeline meat, how it works. Once the spec was signed off, it was time for the pipeline meat. We chose Snakemake because it's modular and data agnostic. Step 1, quantification. We use Salmon for pseudo-alignment. It's significantly faster than traditional aligners like STAR, which was critical for a 2,500 sample run. But Salmon is probabilistic. When the results came back with decimal counts, my gut told me something was off. We pivoted from the initial plan and integrated EdgeR for proper normalization and filtering. Step 2, focusing the data. We didn't just process everything. We used the metadata to isolate colon samples, ensuring we weren't getting noise from different tissue types. Step 3, the p-value pivot. On our initial test set of 15 samples, the standard false discovery rate was useless. I had to pivot the logic to fall back to p-values for the small set, while keeping the FDR logic for the full production. Phase 3, the messy reality. 1 day of debug. Even with a perfect spec, reality is messy. The AI didn't know that a specific version of Salmon had a well-known bug in its index builder. It took me a full day of manual debugging and reading through Salmon's GitHub issues to find the fix and lock our version. To make this work on AWS Parallel Cluster, we containerized everything using Docker and Singularity. This allows us to spin up 100 nodes on the fly, process the data, and shut them down immediately. The AI got us 80% of the way there, but that last 20%, handling the infrastructure and the mess, is where the real value is added. The conclusion, value added. We did this in 14 days. I added value not by being a better biomedical engineer than the expert, but by being the one who could execute the vision without needing constant handholding. The domain expert gave us 4 hours of his time. I gave him back a production-ready pipeline for 2,500 samples. In this new world, you don't need to know every fact. You need to know how to direct intelligence, how to judge usefulness, and how to operate in the mess. Pipeline is live. The results are real. Welcome to Applied Disruption.